All right. Don't look at the bottom of the slide. Just look at the first line. What is the sum of the series 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4? On and on forever. Okay, back to the tablet. Okay. Well, as you look that over, hopefully you notice that I have a negative 1/2 plus 1/2, which maybe I can cancel those, and a negative 1/3 plus 1/3, which maybe I can cancel those. And that's kind of the idea, but you have to be careful, okay? So what I'm going to do, instead of calling this term A1 and this term A2 and this term A3 and this term A4, I am actually going to group these together. This is going to be A1, this is going to be A2, this is going to be A3, et cetera, et cetera. So now let's talk about sequence of partial sums. S1 is just the first term, A1, which is 1 minus 1/2, and I'm going to leave it as 1 minus 1/2. I'm not going to write that as 1/2. S2 is A1 plus A2, which would be 1 minus 1/2 plus 1/2 minus 1/3. And now I am going to cancel the minus 1/2 plus 1/2. So S2 comes out to 1 minus 1/3. And just so I can line these up in a neat little column over here, let me add that in there. S3, which is the sum of the first three terms, I'm going to start writing a little smaller so that my columns line up nicely. Now I'm going to tack on the term 1/3 minus 1/4. And look what happens. Get rid of these, and you can also get rid of these. So the third partial sum is 1 minus 1/4. The nth partial sum then, which is A1 plus A2 plus da 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 all the way to A sub n, that would be 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 until, let's see, you get to the number, at the end you would have a minus 1 over n plus 1. Right? Notice that when the subscript is a 1, the last denominator is a 2. When the subscript is a 2, the last denominator is a 3. Subscript 3, last denominator is 4. Subscript n, last denominator is n plus 1. And everything in the middle is going to cancel. The only things that are not going to cancel are the 1 at the beginning and the minus 1 over n plus 1 at the end. So remember, by the definition of an infinite series, if that series converges, then it converges to the limit of this sequence. And now we have an expression for that sequence. It's 1 minus 1 over n plus 1. As n increases without bound, that expression gets closer and closer to 1. So this series converges to 1. So now let's look at this one. I'll give you a minute to think about that. Well, or just pause the video so that I don't literally have to wait. Right? And at this point, I hear you saying, but Mitchell, this example looks completely different. What am I supposed to do with this? And I say in a teasing way, what do you mean you're having trouble with this? We just did it. All right. Why do I say that? Because 1/2, you can write it as 1 minus 1/2. 1/6, you can write as 1/2 minus 1/3. 1/12, you can write as 1/3 minus 1/4. 1/20th you can write as 1/4 minus 1/5. Oh, so it's the same series that we were just looking at. It's just written in a different form. Well, no need to reinvent the wheel. We know this series converges to 1. Because we just did it. All right. Oh, I was a little disappointed when I flipped to this slide and saw that I didn't have my animations turned on. Kind of spoiled the surprise ending, but you didn't look, right? Okay. Now, before we get to the examples, let me just ask you a question. Does this trick remind you of anything else that we have ever done? You know, taking a fraction like 1/2 and pulling it apart into 1 minus 1/2, or taking 1/6 and pulling it apart into 1/2 minus 1/3. Have we ever had to do anything like that before? Well, the answer is yes, we have. We had to do that in chapter 8 when we talked about the method of partial fractions. That's exactly what we did. So we will be using the method of partial fractions to take a fraction like this and rewrite it like this. And by the way, let me just add one thing. The closed form for this series, let me point out to you another pattern is that 2 is 1 times 2. 6 is 2 times 3. 12 is 3 times 4. 20 is 4 times 5. So you can write this series as the sum n going from 1 to infinity of 1 over n times n plus 1. So whenever you see a series like that, you are going to break that fraction apart using the method of partial fractions. Okay, so let me go quickly over to our examples. And as always, once we look at the examples, we'll go back to the tablet to work them out. So a couple of examples. And by the way, this type of series is called a telescoping series. Imagine a telescope kind of expands out, expands in, expands out. I guess the word is contracts, expands and contracts. So the idea behind a series like this that's got alternating signs that are canceling each other out is the series is kind of expanding and contracting. I think that's why they call it telescoping. All right, so we're going to determine whether each of the following series converges or diverges. If the series converges, we will find its sum. And I'm going to tell you that in general, the only kinds of series where you can actually find the sum are the two that we have talked about in this section, geometric series and telescoping series. Starting in the next section, we're going to look at other types of series where we will be able to tell that they converge, but we won't, unfortunately, be able to find out what they converge to. All right, so here's the first example, the sum n going from 1 to infinity of the inverse tangent of n minus the inverse tangent of n plus 1. All right, and then the sum n going from 1 to infinity of 6 over 2n minus 1 times 2n plus 1. So let's go back to the tablet. All right, so first example, the sum n going from 1 to infinity of inverse tangent n minus the inverse tangent of n plus 1. What I like to do with telescoping series, and there are two indications that it might be a telescoping series. The easier one is the one you see here, that there is a, that the term is a difference So you see that minus in the middle? That means that when you start stacking these things up, S1 would be A1, which would just be the inverse tangent of 1 minus the inverse tangent of 2. And then S2 is the sum of the first two terms. So that would be inverse tangent 1 minus inverse tangent 2 plus inverse tangent 2 minus inverse inverse tangent 3. And those terms are going to cancel. Let's do one more. S3 would be the sum of the first three terms. And actually, why don't I just take down the one that we just did, and then I'll tack on the new term, which is inverse tangent 3 minus inverse tangent 4. Hopefully you see the pattern. The nth partial sum of this series would just be inverse tangent 1 minus the inverse tangent of n plus 1. All right, so if we look at the limit of that expression as n increases without bound, you get inverse tangent 1 minus the inverse tangent of n plus 1. Now, do you remember what happens to the inverse tangent of n plus 1 as n approaches infinity? I'll give you a hint. It's the same thing that happens to the inverse tangent of x as x approaches infinity. Remember the graph of the inverse tangent function? I'll try to squeeze it in here. It has a pair of horizontal asymptotes. And the graph does something like this. Graph gets closer and closer to that top horizontal asymptote, which is y equals what? Do you remember? I don't know if I have room to write it anywhere. It's y equals pi over 2. So this limit is going to equal the inverse tangent of 1, which is pi over 4, minus pi over 2. This series converges to negative pi over 4. All right, next example. The other indication that you might be looking at a telescoping series is when you get something that looks like a partial fraction problem if it was an integration problem. So if I gave you the integral of 6 over 2x minus 1, 2x plus 1, hopefully you would recognize that that is a partial fraction problem. So what we're going to do is take 6 over 2n minus 1, 2n plus 1, and we're going to break it into partial fractions. We have distinct linear factors, so that's going to go a over 2n minus 1 plus b over 2n plus 1. So now if I multiply both sides by the LCD, 2n minus 1 times 2n plus 1, I am going to get 6 equals a times 2n plus 1 plus b times 2n minus 1. Now, even though n has to be a positive integer in the series, that doesn't mean we can't use my trick of filling in convenient values of n to try to solve for a and b. For example, I'm talking about n equals 1/2 would give me 6 equals a times 2 times 1/2 is 1, 1 plus 1 is 2. So this would be 2a plus b times 0. That would give me a equals 3. And when n equals -1/2, I would get 6 equals a times 0 plus b times -2, which means b is -3. So instead of looking at the series n going from 1 to infinity of 6 over 2n minus 1 2n plus 1, why don't we look at the series n going from 1 to infinity of 3 over 2n minus 1 minus 3 over 2n plus 1. And at this point, I'm going to recommend that you pause the video and try to finish this problem the same way that I did letter A. So I'll wait for just a second while you pause the video. All right, so hopefully you've got that all worked out. The first partial sum would be A1, which is 3 over 1 minus 3 over 3, and I'm going to leave it just like that. Second partial sum would be A1 plus A2, which would be 3 minus 3 over 3 plus 3 over 3 minus 3 over 5. So those terms would cancel. Third partial sum would be A1 plus A2 plus A3. And that would be the previous partial sum plus 3/5 minus 3/7. Okay, so we've got a pattern here. The pattern is that in the nth partial sum, the first term is 3, and then the second term is minus 3 over something, and the something is 3, 5, 7, et cetera, et cetera. This is an arithmetic sequence, that 3, 5, 7, et cetera, et cetera. We talked about those in section 10.1. So if n is 1, 2, 3, this denominator is 3, 5, 7, which are going up by 2's. My first guess is going to be 2n, which is 2, 4, 6, but I see that that denominator needs to be 1 bigger than that. So the denominator needs to be 2n plus 1. Okay, I might have overthought that just a little bit. All right. So the limit as n increases without bound of s sub n is equal to the limit as n increases without bound of 3 minus 3 over 2n plus 1. And hopefully it's clear that as n increases without bound, that fraction approaches 0, and that limit is equal to 3. This series converges to 3. The series converges, and its sum is 3. All right. Getting close to the end here. This is a very, very, very important test for identifying divergent series. And I don't want you to misunderstand this, so I'm going to say it very carefully. The theorem says that if the series n going from 1 to infinity, a sub n converges, then a sub n, the nth term of the series, must approach 0. So this is actually more useful in its, what we call in logic, contrapositive, the contrapositive form. Do not use the converse of this. All right. The contrapositive form says that if a sub n does not approach 0, in other words, it approaches something other than 0 or doesn't approach anything at all, fails to exist, then the series diverges. Okay. So again, this test can only be used to identify a divergent series never, ever, ever, ever say that a series converges by the nth term test, because if a sub n approaches 0, you cannot conclude that the corresponding series converges. It may or may not converge. So this is a big, big, big no-no in this chapter. Only use this nth term test to identify a divergent series. All right, a few properties for combining series. If the series a sub n converges to A and the series b sub n converges to B, and I want to point out when there are no indices, which is the plural of index, on the summation sign, then that's an indication that we're only thinking about whether the series converges or not. We're not thinking too much about what it converges to, or it's not important in that particular context. And I'll have more to say about that, I think, on the next slide. All right, but if you have those two series and they converge to those numbers, then the series a sub n plus b sub n converges to the number a plus b. The series a sub n minus b sub n converges to the number a minus b. And the series k times a sub n converges to the number k times a for any number k. All right, and the reason that when we're thinking only about convergence and divergence that the indices don't really matter is because it really doesn't matter where you start the series. And that's because adding or deleting a finite number of terms does not change the convergence or divergence of the series. So the best way to understand that, this makes a lot of sense if you think about it the right way. So suppose you have a series that converges to 10. And you add an additional 500 more terms, or you delete 1,000 terms. By adding 500 terms or deleting 1,000 terms, you are adding or subtracting a real number, because that finite number of terms has to add up to a real number. So it will change the sum of the series, but it won't change the fact that it converges. Similarly, if you have a series that diverges to infinity, all right, think 1 plus 1 plus 1 plus 1 plus 1 forever as a simple example. Taking away 500 of those ones, it's not going to make any difference. It's still going to diverge. All right, so as the final example in this section, I want to talk about reindexing. The series n equals 1 to infinity of 5 over n times n plus 1 can also be written as the sum n equals 0 to infinity of 5 over n plus 1 times n plus 2. Why is that? Well, just look at the first term, for example. The first term, when you write it like this, is 5 over 1 times 2. And it's the same if you write it like this, because n starts at 0, the first term is still going to be 5 over 1 times 2. So in this example, we're going to write this sum beginning with n equals -1, and then n equals 3, and finally n equals 20. So back to the tablet one last time. All right, so here are the two examples that they showed us of how to write this series. So what we want to do in this problem is write it as the sum n equals -1 to infinity. Well, remember that you want this first factor on the bottom, this one right here, to be a 1. So if we're going to use -1, I think the most obvious way to do that is to put an n plus 2 there, and then make this other factor n plus 3. Okay, so the first term will still be 5 over 1 times 2. If you want to start it at n equals 3, the sum n equals 3 to infinity, we want the first factor to be a 1. So why don't we go n minus 2? And you want the second factor to be a 2, so why don't we make that n minus 1? And then finally, starting at n equals 20, can you guess what I'm going to write? We want the first factor in the denominator to be a 1, so why don't we put n minus 19? And we want the second factor to be a 2, so let's make that n minus 18. Reindexing is a trick that sometimes comes in handy in certain kinds of problems. So just wanted to show you a quick example right now. And that's going to do it for section 10.2. We'll see you next time.